Hey, Christian,
Good.
how's it going?
Did email you the slides? Did you see?
Oh,
About 45 minutes ago, maybe.
thought no, I didn't get any email. Okay.
I'll make sure it's not my outbox or something, but yeah, I
Okay.
can send it.
If it's 45 minutes, I think I did check my email within that computer. So could have missed too.
I would send it right now.
Okay.
I don't see my outbox either though, so I don't know.
Okay.
Yeah, so right now the beamer was taking a little bit longer than I expected it to,
Okay.
which is what I typed in the last email.
Was it worth it though?
Yeah,
Like,
it was working.
no, was it worth it? Worth introducing it to you?
Oh
or?
yeah. I'm gonna continue working on it. So
Okay.
that's why I said, but I just finished up the one that I had already made because
Sure.
but I changed it to look more like how it would have came out. But I just did it on PowerPoint really quickly. So
Okay.
I'll send it to you. But yeah, that's why I sent this email. But since I'm here, I'll just.
I had earlier said that I had to meet someone right after this class that got canceled, so we can talk right away if you want.
Okay.
But you can finish and then maybe Friday also is good enough. Best is probably for you to finish and then talk. Right?
Okay.
Let's talk after that. Where are others? 1, 2, 3, 4. So Matt and 4, 5, 6. Matt, wait.
It wasn't signed in. Okay, Jeremy, stop. No, I was not calling you. I was just saying hello, Jeremy. That's all. Yeah. Okay, so we have a homework 5 due. Bowden, I haven't graded yours yet. No point in promising. Intend to. Okay. Finally, let's try, now that we have introduced elliptic integrals, let's go back and try to finish the circular wire using these elliptic integrals. That was the whole idea, because it's a pretty common loop of magnetic field source that we have, and we should have a exact expression, and then from that point on we can move on and try to do dynamics. Okay, so this is circular wire, magnetic field due to a circular current carrying a wire, this time exactly. So this is your current loop. That's the current I in it. That's your z-axis, let us say. And somewhere here is your source. Earlier, we have found the magnetic field due to this when the length from the source point to the center of the circle is extremely large compared to the radius of the wire itself. So the radius is A, and that's your R. And we will also, those are the only coordinates actually, but we will also try to use this as Z and rho. As it comes, I will introduce that. As of now, that's your picture, and the current density we know for this is in terms of the R prime variable. It's in the tangential direction in the cylindrical coordinates. And notice it's prime, so it changes with space points. And there is a current I. And we need current per unit area, right? Current density is current per unit area. The direction is known. And the area is given in terms of delta functions. Delta function area is really small because this is the extremely thin, infinitely thin wire. So you use delta function to represent that. And the delta function is delta of Z prime and delta of rho prime minus A. This much we already used this in various descriptions. The vector potential at the source point R will be mu naught over 4 pi scan for all the sources of current. And the current is at the position described by the delta functions. And scale or weight it by how far the source is from the observation point. So, and that's called the Green's function also. More explicitly, this will be R is mu naught over 4 pi. Done this a few times. dz prime, rho prime, d rho prime, 0 to infinity, and d phi prime. So 0 to 2 pi. And J of rho prime is that I expand that out. And I write phi prime hat, current I, delta of Z prime, delta of rho prime minus A. I'll expand the phi prime also very quickly, but the denominator, if I were to write it in cylindrical coordinates, it is Z minus Z prime square plus rho square plus rho prime square minus 2 rho prime times cosine of phi minus phi prime. Again, we have done this a few times, so I will go into the details of what that denominator, where that appears from. Two of the integrals is straightforward, Z prime and rho prime, and we get this is equal to mu naught over 4 pi. Rho prime gets replaced with A, and that is an I, A times I, and that is the integral on phi prime. I've taken care of most of the numerator except the unit vector, and I explicitly write that unit vector. That's minus sine phi prime in the I hat direction plus cosine phi prime in the j hat direction divided by Z prime is set to 0, so it's Z square plus rho square plus rho prime is set to A, so it's A square minus 2, so this is rho prime. It's 2 times rho A cosine of phi minus phi prime. Right, that's your complete expression. And recall that, so that's all we can do. We cannot proceed from here. One way we proceeded was to make an approximation. We said that this is, remember, R also, right? This is R, how far your source is. If this was very large compared to A, then there was an approximation that we found. But in general, this integral is not doable. That's where the elliptic integral comes, but we have to process this into that form. So let me. So I have to be able to write this in terms of the elliptic integrals. What are the elliptic integrals? K is equal to 0 to pi by 2 d psi 1 minus that's one of the elliptic integrals, the complete elliptic integrals. And the second elliptic integral is k e of k. That's 1 minus k squared sine squared. So it is not at all in that form. But there is a hint here that cosine phi can be written in terms of half angle formula, right? So sine square shows up there. But this is running from 0 to 2 pi, so this is running from 0 to pi. So we have to do some processing, and that is all that is needed. So the whole point would be to rewrite this integral in terms of these two integrals. We are not going to evaluate it. It's mostly going to be algebraic in the sense of sort of massage it so that this can be pushed into that form. So that's our goal. So let's start by substituting. There is a cosine of phi in here. I should be able to move that off. So let's substitute phi minus phi prime. So let's substitute here phi. I can substitute phi prime also. Right? So phi minus, let's say phi prime minus phi is equal to phi double prime. Like if I substitute that, this becomes phi double prime, and instead all this will move into the numerator. And let me do that. So this is d phi prime is equal to d phi double prime, and my limits will go when phi prime is equal to 0, phi double prime is equal to minus phi. And when phi prime is equal to 2 pi, phi double prime is equal to 2 pi minus phi. So how does my vector field change, vector potential change? So that's equal to A, or it's equal to mu naught over 4 pi times A, right? And this becomes minus 5. Wherever it's 0, that's minus 5. That's 2 pi minus phi. And this is d phi double prime. And I get minus of sine phi prime is phi prime, phi double prime plus phi in the I hat direction plus cosine of phi double prime plus phi in the j hat direction. correct? And divided by the denominator, now that's r square plus a square minus 2 times rho times a. Notice r square is rho square plus z square. Cylindrical coordinates and spherical coordinates are related that way. And our denominator has this nice feature, that's the side of phi double prime. Let's process this unit vector a little bit. So the square bracket, which is the unit vector quantity that I have written there, that's actually can be written as, let's expand that out. Let me explicitly do that. So that's minus of sine phi double prime, cosine of phi in the I hat direction, minus of cosine of phi double prime, sine of phi in the j hat direction. And we have plus cosine phi double prime, cosine phi in the j hat, and minus of sine phi double prime, sine phi. Oops, this is I. Right, okay. Collect the phi primes together, and what we get is, if I were to collect minus sine of phi double prime, I get cosine of phi I hat, that's this one. And the second one is the last term, so that's sine of phi in the j hat. And similarly, I collect the cosine of phi double prime, and that's minus sine phi I plus cosine phi j hat. But this is, you will identify that this is a unit vector, the cylindrical radial unit vector, but this time with respect to the source coordinates. We started with the observer coordinates. We started with the source coordinates, but we are able to convert this into observer coordinates. So this is equal to minus sine phi double prime times rho hat plus cosine phi double prime times phi hat. But again, notice this is not primed quantities, these are unprimed quantities. So put that all together, and we are left with two integrals now. And I will also do one more thing in here. Notice this is an integral that's running from minus phi to 2 pi minus phi. That is the whole of the range of phi. And this is a summation. When you are summing things together as far as it is convergent quantities, whether you do 1 plus 2 plus 3 or 2 plus 3 plus 1, it doesn't matter. So I can again go back to 0 to pi, and that's perfectly fine. In fact, I will go from minus pi to pi. So this is equal to r is equal to mu naught over 4 pi times a I, and I'll go I'll do two things. I'll actually take a rho hat comes out of the integral now. So that's so it's a minus sign, mu naught over 4 pi a I rho hat, and minus pi to pi d phi prime. So that's the sine phi prime. And we have r square plus a square minus 2 over a. Okay. And that is one more integral plus is this within the, yeah, plus mu naught
phi hat. This is cosine. Okay. Notice what are we talking about here? We are talking about the electric potential due to a circular current carrying wire, and we should ask ourselves what is typically the direction of the vector potential. Go back to your straight wire. So if you have a straight current carrying wire, what is its magnetic field? The magnetic field lines are circular, right? That's your B. That's your B field. But what's the direction of the vector potential? It's in the same direction as current, so vector potential is usually like this, right? They get weaker and weaker as you go farther and farther. That's A. Vector potential is usually, if it is a steady current in the sense, even in the direction sense, that it has a very symmetric current distribution, then all the contributions just add up in the direction. So similarly, if you have a circular wire, if the direction of current is given to us, so the idea is that A will also have the direction of the current. That's not a theorem in the sense that always it's the case. You can always imagine there will be two sources, one in a plane and one is not in the plane, then they will add up and they will combine together in different forms. But if they are simple configurations, they always have. Which means that A should be in the direction of phi hat, right? Probably. There should be no rho hat contribution in that. That seems to suggest that maybe this is zero. How can this be zero? Probably this integral is zero, right? So how do we, can we really show that? So let's see if we can motivate that. For that purpose, we already know that this integral goes from minus pi to pi. So let's split it into minus pi to 0 and then 0 to pi. So let me consider this is minus pi to 0 d phi prime double prime, and we have sine of phi double prime cosine. Let us substitute in this. You want to somehow convert this into 0 to pi. It is already clear that it won't contribute in the sense that sine of phi changes sign, right? So sine of phi is anti-symmetric. This is symmetric. So if I were to change phi prime to phi double prime to minus phi triple primes, let's say. So this becomes d phi double prime is equal to minus d phi triple prime. So what does this integral become? When phi is equal to phi double prime is minus pi, this becomes plus pi. Whenever it is 0, that becomes 0 again. D phi double prime is minus d phi triple prime. Sine of phi, when you replace it with a minus quantity, it becomes minus of sine of triple prime. And cosine does not change sign, so it stays the same. So minus and minus goes away, and so this is exactly equal to minus of 0 to pi. Like minus signs cancel out, and I flip the sense of integration, then it becomes minus. which means that this integral has to be 0, because if you go from minus pi to pi, you have just now shown that from pi minus pi to 0 is exactly this, the negative of going from 0 to pi. So overall, this integral is gone. So the rho prime integral is gone. So this whole thing is 0. This integral is equal to 0. We can argue the same thing on the cosine phi also. Like this will go identically, like this will go from pi to 0, there will be minus d phi prime, but there won't be this minus sign there. Right? This minus sign will not be there, and because cosine function is even, so you won't get minus. So instead, what this is equal to is it's 2 times 0 to pi. Is that clear? Right? Because this will be symmetric, it will be exactly 2 times 0 to pi. Any questions on that? Is that very clear? Okay, if you allow me to do that, then what we have learned is, so maybe I should write that down, just so that I can actually write that down. So minus pi to 0 d phi double prime of cosine of phi double prime over square root is exactly equal to 0 to pi. And the square root means is exactly the same. So using that, that means this can be broken into 2 times that. So what I have is that the vector potential then is equal to factor of 2 that comes out. So you have mu naught over 4 pi times 2ai times phi hat direction, and this is 0 pi phi double prime and cosine r square plus a square. Our goal is to write this. Remember, we are not doing anything substantial here. We are just processing this integral or rewriting this integral in a form where we can really identify the elliptic integrals. There's one more thing we need to do that is very straightforward. We could have actually done it in the first step itself, combined it in a sense, but we want to make this to 0 to pi by 2, right? Because that's how elliptic integrals are defined. So replace phi prime, phi double prime. Instead of going to triple prime, let us just call it psi. Right? So it's psi over 2. So d phi double prime is d psi over 2. So this is equal to naught over 4 pi 2 a I at when phi prime is equal to 0, psi is equal to 0. When, oh sorry, I think what I wanted to do was the opposite, right? So I want to substitute psi is equal to phi prime over 2. So 2 times d psi. Okay, sorry about that. So when phi prime is 0, psi is 0. When phi prime is equal to pi, this is equal to pi by 2. d phi is 2 times d psi. And rest everything is the sine of psi by phi prime is 2 psi. Right? Great. And then we use our what is this called? Double angle formula. It's mu naught
over 4 pi. So 4 times A times I times phi hat 0 pi by 2 B side. And cosine of 2 side is yeah, it's 1 plus, correct? 1 plus sine, no, what is this?
Cosine 2 theta is 1 minus cosine squared. Or no, cosine squared is 1 minus cosine 2 theta over 2.
So cosine square theta is 1 plus
It's
1 plus cosine 2 theta over 2, and sine square theta is 1 minus cosine 2 theta over 2. So cosine 2 theta is 1 minus 2 sine square theta, 1 minus 2 sine square psi. Correct? That's what I was looking for. Thank you. So this is r square plus a square minus 2 times a rho. This is 1 minus 2 sine square psi. Almost there. So now we have the structure showing up, right? Of sine of the elliptic integral. Let me pull out this whole, or let me write one more step, maybe it is much more clearer. Mu naught over 4 pi, anyway, processing. Pi hat times 0 pi by 2 inside. And let me pull that whole thing out, or let me, yeah, that's what I said, I will write it. 1 minus 2 sine square psi divided by, this is r square plus a square minus 2a rho. There's a plus 4a rho sine square psi. Remember your K and E. We want E is 1 minus K square sine square, sorry, and K you see that in this form, except that I have to pull this out, right? I have to make this a 1. But I can pull that whole thing out because that's not independent on psi. So it's convenient for me to define, let me define K square as, once I pull this out, I should do that in the next step. So that's mu naught over 4 pi times 4 times a times I divided by whole thing is being pulled out. That's phi hat, and this is 0 to pi by 2. Let's go slow. 1 minus 2 sine square psi divided by 1 plus 4a rho over r square plus a square plus minus 2a rho. Hopefully that's clear now why I defined that or why I'm going to define this, because then this is identical to that. So this is 4a rho. Let me define this to be r square plus a square minus 2a rho. Remember, this is also equal to often written as 4a rho over z square plus rho square plus a square minus 2a rho, which is the same as 4 times a rho divided by z square plus rho minus a. Minus or plus? Yeah, this is. Oh, help here. What happened to the problem? Oh, what happened? There's a small challenge here, right? Because this is plus, correct?
Yeah, it's because when you substituted 1 minus 2 signs, right? Oh, no.
It is plus, correct?
Yeah.
Yeah, so it is plus. So I have to show something now, right? Okay. So let me not process this here. So I want to go back to this point. Okay. So this is all wrong. Absolutely nothing wrong in this, but this is not very useful because I wanted a minus sign here. Right? So I should be able to show somehow that this is also equal to some plus form of this, so that we should be able to substitute something there and be able to show that. So let's go back and try that. So let me take this integral and go here. So let's process that integral a little. Oh, what happened here?
That's okay. Postpone it.
Okay. So let's go back to this integral and see. So let me say this is the integral I, and 0 to pi d phi double prime times cosine. Oh, did I move the camera? So I'm just copying that integral there, and then I'll move the camera so that you can see. That's 1 r square plus a square 2a rho cosine of phi double prime. The point is, this is perfectly fine, but when I substitute this 1 minus 2 sine square psi, it did not flip sign and it doesn't help me much. So I want to do some processing there. So the idea is, what can I substitute so that I change this sign so that sine square comes with a positive sign. So cosine of what is negative. So let's try phi double prime is equal to pi minus phi triple prime. So that way I will have phi triple prime will be equal to pi minus phi double prime. So whenever the top is pi, or this will be cosine of phi double prime will be cosine of pi minus phi triple prime, and cosine of pi minus some quantity is the cosine itself with a negative sign. Right? So that's the idea, and preferably the limits stay the same. Let's see. So when phi double prime is 0, this is pi, and when that is equal to pi, that goes to 0, and I'll be able to flip. So this is d phi double prime is equal to minus d phi triple prime, so it's minus triple prime, and this is cosine of pi minus phi triple prime, and this is r square plus a square minus 2a rho pi minus triple prime. Use the negative sign to flip it, flip the integrals, integral limits, and cosine of this is a negative sign, so that's important. That is a negative sign that's coming in. Otherwise, it is the same cosine phi triple prime, and I have
r square plus a square. This becomes plus 2a rho. So everything's same. So if I switch the sign here, I can switch the overall sign. That's the way it is working, right? So if I flip the sign in the denominator, I have to flip the overall sign. So I'm going to use this result back, and instead of redoing the whole thing, I'll just put in the signs if you guys don't mind. Right? So we'll go through the same process again, but change the sign here and change the sign, overall sign. Okay, going back then is so I'll circle them. So this is I change the sign to plus, and this becomes a negative sign. Overall negative sign, overall negative sign, overall negative sign, and this becomes positive. Oops. This stays the same. This becomes positive. This becomes positive. This becomes negative, and that's an overall sign there. And I just have to write it down. Is that clear? Did I confuse? Was it reasonably okay? Did you guys follow?
Yeah.
Okay.
Yeah.
Yeah, okay, thanks. Okay, so that's an overall sign of minus sign now. This is okay, and this now is minus sign. And this will be plus. So my k, I will define it as plus. Yeah. So this is plus, so this is plus. So that's different forms of writing here. Okay, great. So we have minus mu naught over 4 pi times 4 times a times I divided by r square plus a square plus 2a rho square root of that. And this is nothing but phi hat. Now let's process this. The first term clearly is 1 over k square sine square. That's k immediately. So
It's a row, right? 2a row.
oh, 2a rho. Yes, that's good. Okay. So let me write this explicitly. 0 to pi by 2 of d side 1 over 1 minus k square sine square psi. That's the first term here, minus. And the second term is minus 2, and it is 0 to pi by 2 d psi. And I want to leave some space here. So writing the sine square side, leaving a little space. I want to do some manipulation in the numerator there. So leave some space there, sin square psi and 1 minus k square sine square psi. That should be okay. I can process this a little bit. So what I do is that I do a k square here and divide it by k square. That's perfectly fine because k square doesn't depend on psi. I even take this negative sign in, make that positive, so that it looks like the elliptic function. Then I add a 1 there and subtract a 1 there. That should be perfectly okay. That way, what happens is that this now this is having an elliptic feature there, but we have to divide that out by this. And this, on its own is a k. It's a k elliptic interval. So overall, what is this equal to? This is minus mu naught over 4 pi 4 times a times I square plus a square plus 2 rho, the phi hat direction. That's a k. That first piece. Second piece is plus 2 over k square, and there is a minus of k. That's the first piece. And the next piece is plus integral of 0 to pi by 2 d psi 1 minus k square sine square psi. But that's in the denominator also, so this becomes this, which is exactly E. So we have got the result in a sense. We have expressed our answer. Just basically mostly algebra. Return our result in terms of elliptic function S. So this is k. So this is plus 2 over k square minus k of k plus e of k. So it's not very insightful, but that's expected. This is an exact result. For insight, we need to make some approximations. But this has this feature that you can plug in the observation point to be anywhere you want, and you have an exact result. We'll come back and actually make some processing of this and try to get some feel for what this is. But also remember that once I have A, this is all vector potential, right? It's an exact solution for the vector potential. And this probably will, or actually maybe we can do one thing. But before that, I should say magnetic field is the cross of this, right? Derivative, take the derivatives, and that will be. Let's do one thing actually that is good to see. We do know that the vector potential, let's say, right on the axis, right? Yeah, let's not do that because that will be. Let's do the next. Yeah, be more careful. Yeah. So let's do that next time. So I was thinking we can take some limits and see, but we have to be careful because this is 1 over something. So that is a apparent divergence that we should clarify what that is. Yeah. I'll come back and do a little bit of, you can say, taking limits of this expression in various ways, or just basically on the axis, and get some insight of what this means. And from then we can proceed to other. Actually, one thing I want to do before we go into dynamics is what is magnetic energy. Right? We have talked about forces a lot. We have talked about magnetic field, how it is created, but we have not yet made things interact. Right? So what is the magnetic energy? So we should have a feel for that. We might have, what's the work done by a magnetic field on a charge? If a charge is moving in a magnetic field, what is the work done by the magnetic field? Magnetic force or magnetic field? Might be a familiar concept. It's a popular concept also in a sense. Remember the work done by, quiz, right? We have not had a quiz for some time. What's the work done by a magnetic force on a moving charge? Remember F dot dl, that's how you calculate the work done. And if the force was QV cross P, then what's the
So it'll be 0.
0? Yeah, good. So it will be 0. So what does that mean about the magnetic energy?
It's also 0. It's just,
But then nothing should happen, right? If,
oh. Oh, so that way, like the square comes in, like it's like the expectation is 0.
no, this is more than that. Actually, it's not 0. Magnetic energy is not 0. There is magnetic interaction possible. But this is like something like rolling. Whenever you have this rolling, right? What is the work done by friction in the rolling? Like when a ball rolls about an incline. Have you done this calculation? What is the kinetic energy at the bottom of the incline? You do energy conservation principles and get that, right? You know what I'm talking about?
So like equating it to the potential at the top.
Yeah, the kinetic energy at the bottom will be equal to the potential energy on the top, right? Now, typically, if you notice that problem, that is rolling actually. And rolling requires friction. So there's friction on the problem. But when you are doing conservation of energy, you never bothered about friction. What happened to that? How can that be right? But it is right there. It is exactly correct there. And the idea is that whatever energy you lose in the linear motion, you gain in the rotational motion. Very fine cancellation happens there. So friction, you don't lose anything in the friction. It's kind of interesting there. So similar things happen here. It's not very, it's just an analogy, not exactly related. There is magnetic energy, but there is also a magnetic momentum. So you don't gain any energy, but you're actually changing momentum. So all the work, all the energy is being used up, if you want. Not really energy. How would you say? It's conserved in the sense that it is changing its momentum. But let me stop here. We'll come back and do this in a reasonable, in a proper way. I'll introduce that. That should clarify this point. Okay. So yeah, so we didn't have a quiz on Monday, I think. Right? So
I think there's 2.
okay. So we did have a quiz. Okay, good. Okay, then that's good. Yeah. Okay. Okay. Thank you. Yeah. Bye.
So the question was work done on magnetic fields by a moving charge.
If you have a moving charge in a magnetic field, what is the work done by the magnetic force? Yeah, that's the definition. That's how you say. What's the work done by the magnetic force? That's all.